Assalamualaikum and very good day to everyone. Okay, as per last class, we have discussed on the basic fundamentals of thermodynamics. Okay, we have discussed on the superheat, superheat uh, water. Okay, and also compressed liquid. So today we proceed with the ideal gas equation of states. Okay, so ideal gas equation of state. So basically we need to determine first what is by the definition. What is equation of state? Equation of state means any equation that relates the pressure, temperature, mass and volume of a substance. So basically you can look into the figures on your right, a balloon. So basically the balloon has a constant volume. Okay, if we increase the mass of the uh, air inside the balloon, so basically it also will increase the pressure. Okay, so basically we can have this equation lah. So pressure with correlation with your mass. Then when the pressure increase, the temperature of the gas inside the balloon also increase perpendicular. So but when we reduce the volume of the balloon while the mass is we keep constant, the pressure also will increase. So we have pressure is 1 over volume. So combine all these character, we can get that your pressure is mass times your temperature is divided by volume, and we convert into the mathematical form. We got R here. R we call it as a universal gas constant. Basically we need some constant in order to have your pressure equivalent to your mass, temperature and volume. And also your universal gas constant R is a proportionally constant and depend on the nature of the gas. Maybe we talk here air. Air we got 0.28 something kilojoule per kg dot Kelvin. Okay, but for any other material, the value of universal gas constant R is different. Okay, so we arrange the equation. We got PV equals to MRT. Okay, where your pressure P in kPa, your volume in meter cube, temperature in terms of Kelvin, and mass is kg, and ideal gas constant in kilojoule kg dot k Kelvin. Okay, so basically here if you got any other units, for example pressure we got in bar, we need to convert it first to Pascal. Same with temperature. If you got a problem with temperature in degrees Celsius, so you need to convert to Kelvin first. Okay, so in order to make the equation applicable to all ideal gas, the universal gas constant Ru is introduced. Okay, so basically if you have any other rather than air, okay, so you need to have a Ru lah. So your universal gas constant is equivalent to Ru divided by M, where your Ru is universal gas constant kilojoule per kilomole dot K, and your molar mass kg per kilomole. So rearrange. You got your for air, this example air, so you got Ru air 8.31344, and for air of molar mass air is 28.96. So you got 0.2871 kilojoule per kg dot Kelvin. So for ideal gas, equation of state also can be written as in terms of number of moles. So here we got PV equivalent to number of moles and Ru times temperature. Okay, so the ideal there are three names in particular they associate with ideal gas law. Okay, so basically we got Robert Boles, okay, Jack Charles, and J.L. Gay-Lussac. Okay, for Boles law, the temperature we assume to be constant, so we got PV equivalent to constant. Charles law, the pressure is constant, so we got V per T is constant, and by Gay-Lussac's law, the volume is constant, so you got P over T is constant. Okay, so untuk example problem 2.12, an ideal gas is contained in a closed assembly with an initial pressure and temperature of 220 kPa and 70 degree respectively. If the volume of the system is increased by 1.5 times and the temperature dropped to 15 degrees Celsius, determine the final pressure of the gas. Okay, given directly the pressure 1, P1 equivalent to 220 kPa and T1 is 70 degree Celsius. Alright, and also given in the example will be the volume V2 is 1.5 V1, and also the temperature drop T2 drop 15 degrees C means it's about 55 degrees Celsius. Okay, so determine the final pressure. So this example is on ideal gas equation of states. So by using the ideal gas equation, PV is equal to mRT, whereby your R is universal gas constant, which is 0.2870 kilojoule per kg dot Kelvin. Okay, so the correlation between the state 1 and state 2 is based on the volume. Okay, so we can do a equation P1 V1 M is equal, the mass is equal for mass 1 is equal to mass 2, so therefore RT1 equal to P2 V2 RT2. As the universal gas constant is similar, so we move out. So only P1 V1 equal to T1 equal to P2 V2 T2. Alright, so the question is to determine the final pressure P2. Rearrange the equation. So you got P1 V1 equal to T1 times T2 V2. Okay, as V2 is equivalent to 1.5 V1, so you can add in your equation. So P1 220 kPa, T1 70 degrees Celsius times T2 55 degrees Celsius 1.5. Okay, so you got the final answer kPa. Okay, thank you. Example problem 2.12. Example problem 2.13. Alright, so we move on into example 2.3. Okay, an automobile tire with a volume of 0.6 meter cube is inflated to a gauge pressure of 200 kPa. Calculate the mass of air in the tire if the temperature is 20 degrees C. Okay, so given directly is the volume V 0.6 meter cube inflated at a pressure P 200 kPa and the mass we want to calculate, and the temperature is T is 200 degrees Celsius. So is an ideal gas equation of state. We use a formula for ideal gas equation. So PV MRT, as your universal gas constant is 0.2870 kilojoule per kg Kelvin. Okay, so therefore P given, volume given, and also temperature is also given. So your mass pressure is 200 kPa gauge times volume 0.6 meter cube divided by 0.2870 kilojoule per kg dot cube times temperature 200 degrees C, convert to Kelvin, okay, so potong kilojoule as joule is joule, Newton pressure, kPa, sorry, pressure times alright, so as joule is Newton meter is equivalent to P Pascal times, this is your Newton and meter, so substitute into the equation above, so kilo J ni, so here you got PA meter square, so left all is left only kilos, so you got your kg. Okay, thank you. Example problem 2.14. Okay, sample problem 2.14. Determine the number of mole and mass of helium fills in 381.7 meter cube container at 200 kilopascal and temperature of 300 K. So given directly is volume. So the volume is 381.7 meter cube. The pressure is 200 kPa and the temperature is 300 Kelvin. Okay, so this is the in the molar mass state, so therefore we use the condition as PV is your N number of moles times RU. RU is a ideal gas constant for air, and temperature. So RU is 8.3144. Okay, kilojoule per k mol dot k. Alright, so what we want to find is number of moles. First, n value. Alright, so rearrange the equation. N is PV RUT, so equivalent to 200 kPa times volume 381.7 meter cube point 3 times RU 8.3144 kilojoule per kmol dot K Kelvin times temperature is in Kelvin 300 Kelvin. So hitung. Okay, so we got only kilomole. So n is in kmol. Alright. So as in the slide, we know that for mass, number of mole mass for air is 28.96 kg per kmol. So mass of air is m times n, 28.96 kg per kmol times kmol. So you got your answer in kg. Okay, thank you. Okay, as we see the example above, so we proceed with specific heat. Okay, so what is a specific heat? It's a motion of substance requires energy. The more energy substance, the higher the temperature it will also have. So this typically energy is supplied by heat. Maybe you can find any other form of energy, but in this example we introduce heat lah. From that heat, energy is increasing. Either heat loss or gain by substance is equivalent to energy loss or gain. So specific heat is another physical property of substance. All substance has a temperature associated with it because we tolerate with heat. So the temperature of substance is a direct measure of the motion of a molecules. The greater the motion, the higher the temperature, as shown in figure below. Okay, so this is low movement with low temperature, higher movement with higher temperature. So with the observation below, we understood that we can now ask the following question: by how much will the temperature of the substance increase or decrease by the gain or loss of heat energy? So the answer is given by the specific heat of the object. So the temperature heat, the specific heat of an object is defined as the energy required to raise the temperature of the unit mass of substance by 1 degree. In mathematically, we got C, specific heat, energy, kilojoule, divided by mass, kg, times your difference in temperature, Kelvin. So we got two kinds of specific heat. So the first is specific heat at constant volume, Cv, specific heat at constant pressure, Cp, and it does not involve phase change process since the temperature does not change during this process. The first we talk about specific heat at constant volume, CV. So the energy required to raise the temperature of the unit mass of a substance by 1 degree as the volume is maintained constant. So here the keyword is volume. So basically the energy required to raise the temperature while your volume is constant. So we consider a rigid tank. So in the figure side, so when the heat is added, Q in, into the tank, the pressure, the temperature, and internal energy will also be increased. The pressure, internal energy, temperature is increased, but your volume is constant and your mass also remain the same at 1 kilos. So note that the substance is relatively not flowing. It's a closed condition. The change of internal energy due to heat added and temperature of this process can be visualized as UT diagram aside. So you got here is the internal energy, temperature in Kelvin. So you got a constant volume line here. So your increment is your du. So this here increment also we got dt. So the slope of the constant volume is the specific heat at a constant volume, CV, can be represented mathematically as CV du over dt, and therefore the internal energy can be approximately calculated as du CV dt, or simply as internal energy U CV times temperature T. So we move on into another constant pressure, specific heat at constant pressure, CP. So basically, what is the specific heat at constant pressure? Is the energy required to raise the temperature of unit mass of a substance by 1 degree as the pressure is maintained constant. So consider a piston cylinder device shown in a figure aside. Here, when the heat is added, heat Q in, okay, when the heat is added into the cylinder, the volume, the temperature, the internal energy will increase as the piston and push the piston move forward, which means that from initial condition 1 to final condition 2, the volume is changing, but the pressure remain constant. So note that the substance is flowing and the change of internal energy, pressure and volume can be seen as enthalpy. So therefore your enthalpy is equivalent to internal energy plus pressure times volume. So the change of enthalpy due to heat added and temperature of this process can be visualized as enthalpy temperature diagram side. So this is your linear increment. So the slope here of the constant pressure line can be represented mathematically, okay, Cp dH over dt. So therefore the enthalpy can be approximately calculated as, so dH Cp times dt, or simply enthalpy equivalent to Cp times temperature. So we have three ways of calculating the difference in internal energy and difference in enthalpy. So we can, using the tabulated internal energy and enthalpy data, This is the easiest and most accurate way when the tables are readily available. Also, we can using CV and CP relation in appendix table A to C as a function of temperature and performing the integration. So this is very inconvenient for hand calculation, but quite desirable for computerized calculation when you do a numerical analysis. So the result obtained are very accurate. So here it does something like this. Okay, by using average specific heat, this is a very simple and certainly very convenient when property tables are not available. The results obtained are reasonably accurate if the temperature interval is not very large. For real gas, the value of Cp specific heat at constant volume and Cp specific heat at constant pressure will vary with temperature, and it is usual practice to use average value in a given temperature range. So here in scope MEC 451, we will use average specific heat, which means that the temperature is in average value. So the relation between your Cp, Cv and R, okay, and also specific heat ratio K. Based on the enthalpy, we know that your enthalpy UH is internal energy plus pressure times volume. So for ideal gas, PV is equals to RT. Then H is also enthalpy is equivalent to internal energy plus RT, universal gas constant, times temperature. And then you differentiate the above equation, you got something like this. So knowing that for ideal gas, enthalpy is CPT and your internal energy CVT, also your Cp and Cv are constant, then the equation can be rewritten as Cp dt is equivalent to Cv dt plus R dt. Divide the equation by dt, we got Cp equivalent to Cr plus Cv plus R, or Cp minus Cv is equivalent to R, universal gas constant. So the specific heat ratio K, maybe some other textbook denotes as Y, is the ratio of Cp over Cv, or simply written as K, equivalent to Cp over Cv. Alright? Okay, so we look into the example. So example problem 2.15. Okay, sample problem 2.15. Exhaust gas leave the exhaust pipe of a motorcycle with a pressure of 1.2 bar and temperature of 400 degrees Celsius. If the specific heat of the gas at constant pressure and constant volume are 0.912 kilojoule per kg dot Kelvin and 0.684 kilojoule per kg dot Kelvin respectively, determine the density of the exhaust gas. Okay, so directly given here is the pressure. So pressure is 1.2 bar and the temperature is 400 degrees Celsius. Okay, and the Cp is 0.912 kilojoule per kg dot Kelvin. Cv is 0.684 kilojoule per kg dot Kelvin. Okay, so determine the density of the exhaust gas, the rho. Okay, something like this. Okay, the first thing we should do is that we need to convert the bar into the kPa. Okay, so as this we assume as a ideal gas equation, so we get PV mRT. As we want to know what is the value of the density, we have a volume, we have a kg, kilos, so P is rho RT. Okay, so we don't know yet what is the value of universal gas constant, because here we assume that normally we assume universal gas constant R is 0.2870. That is for air. So here, as we don't know what is the exhaust gas, so we need to determine what is the value of R. So universal gas constant R is Cp minus Cv. So we got here okay, so you can get the answer lah, kilojoule per kg dot K. Substitute into your general equation, so you got your rho is equal to your pressure. You need to convert into here, so you can get what is your P RT. So you can get your answer directly lah, kg per meter cube. Alright, okay, thank you.